Hey everybody, I wanted to post a short video to help you out with homework 17, which we discussed before the break, and some of you let me know that you don't have your notes, and so the homework is a little intimidating for that reason. So I wanted to do that. Homework 17, which let me get up here real quick, uh, is over basic numerical quadrature, and the preamble to the homework summarizes the basic methods that we talked about, the trapezoid rule, the midpoint rule, and Simpson's rule. And it gives an error bound for each one. And then in the homework, I ask you to apply those concepts to figure out how to estimate this integral, integral from 0 to 1 of e to the x cubed over 3, using those rules. What I specifically ask you to do is to figure out how many subintervals it would take for each of the rules in order to achieve an accuracy of at least 10 to the minus 6. So I had a little example. Actually, I'm going to use the same example that I used in class, or at least part of it. Uh, in class, we worked through the integral from 1 to 3 of e to the minus x squared over 2 using all three rules. Let me just do it using Simpson's rule in this short video, and then we can, I think you'll be able to see how to apply the same concepts apply to the other two rules as well. So there's going to be two steps in doing an estimation problem like this. First, determine the number of subintervals required for the accuracy that you're asked for. And then second, actually compute the estimate. And I should say here that actually in the homework, I only ask you to do part A. I don't ask you to actually compute the estimate, just figure out how many subintervals it would take. But here we'll go ahead and do both parts just for completeness. So the key idea is going to be that error estimate, which for Simpson's rule is right here, and again that's in your homework. Notice this constant M4 that is part of the error bound. That is the maximum value of the fourth derivative of whatever function you're trying to integrate for x running across the integral, the interval of integration. So that's going to be the key that allows you to determine the right number of subintervals and then actually do the estimate. So let's look at this one step at a time. We'll first determine the number of subintervals. So we just plug in the values we have for our function. The region of integration is from 1 to 3, so my b is 3, my a is 1. And we get this, and then a lot of the work is really in determining these constants, the M4 in this case, which will be the fourth derivative of the function I'm trying to integrate, so that's e to the minus x squared over 2, in absolute value, and I want to maximize that as x runs across my region of integration from 1 to 3. So the first thing you need to do is calculate that fourth derivative. There's a little bit of work involved there. But I think in the homework, I actually go ahead and give you what the fourth derivative is, so you won't have to pull your hair out calculating 4 derivatives of that thing. But that's the guy that we want to maximize. Actually, we want to maximize its absolute value. When you're maximizing the absolute value of something, that could eat the maximum value of the absolute value could be a minimum value of the original function. And so it's oftentimes in doing these kind of problems, you want to just first look at the function itself and then put on the absolute values. And so that's the approach we'll take here. To maximize my function, this guy, I'd want to look, or minimize it, I'd want to look at the critical points, which are this. That means I would look at the derivative of my function and set it equal to 0. And if you do that here, here's the derivative of my fourth derivative, which I'm computing critical points of the fourth derivative. So I set that derivative equal to 0, and then I try to solve. E to the minus x squared over 2 is never 0. I could make this derivative 0 by making x equals 0, but x equals 0 is not in the interval from 1 to 3, so it's irrelevant for this problem. The other possibility is that this guy could be 0, this quartic. So I set that up. Usually solving quartics is difficult, but in this case, this guy is actually quadratic in x squared. In other words, if you let y equal x squared here and write the equation in y, you get a quadratic, which you can solve using the quadratic formula, and I've just done that real quick here. And then once you got the solution for y, x is, of course, just plus or minus the square root of y, and so we get these as possible critical points for our function. But then again, we throw out anything that's not in the interval from 1 to 3, and so that would throw away the minus sign there. And it turns out that both of these remaining points, 5 plus radical 10, all taken the square root of, or square root of 5 minus the square root of 10, both of those are in the interval from 1 to 3, but the maximum of the absolute value actually occurs at the 5 minus radical 10 under the radical. One way to see that is to, you can just kind of work through it, but you can also just graph the function you're trying to maximize. I'm doing that here. The red curve is the fourth derivative without the absolute value, and the blue curve is the fourth derivative with the absolute value. And so you see that maximum value is occurring right here at about 1.3 something between 1.35 and 1.4. That is that radical 5 minus radical 10 over that we saw before, this guy right here. That's that critical point, and he's providing the maximum of the absolute value of the fourth derivative. So next we would plug that value of x into the fourth derivative to find out what m4 is, and of course take absolute value before that. So taking that x we found, plugging it into the fourth derivative, and then taking absolute values, and that winds up at 1.8549. So that's my value of m4, at least rounded to 4 places. Once I have the value for m4, I can use that. I can then use that in my error estimate. So remember, this was my error estimate. That's my m4, and I just rounded it up to 1.86 to make the numerics a little bit simpler. And I want that error to be less than 10 to the minus 6. And so now you just solve that little inequality for n, and you get n is 27.9799. I'm sorry, 23.9799. Now, we remember for Simpson's rule, you need n to be both an integer and even. So in this case, we'll need n to be 24. The other two rules don't require n to be even, but Simpson's rule does. In other words, if this had been 24.97, we would have had to round up to 25, and then we would have had to go on up to 26, because for Simpson's rule, n needs to be even. But in the situation at hand, n equal 24 will suffice. And really, that's all I wanted for the homework 17. But just for completeness sake, let's go ahead and use that to compute the estimate. Once you have the value of n, then you can compute the nodes, the node spacing, which is delta x. That's just your interval length divided by n. Then you can compute the nodes, the x values where you're going to be computing values of the function, as just your lower bound plus k times the delta x value, as k runs from 0 to n. And for us, that would be 1, because the lower bound of our integral was 1. And then our delta x is 1 over 12, so k times that is k over 12. So those are our nodes. And then Simpson's rule would give this estimate. Where's that coming from? Well, that's coming from, let me pop open the assignment again if I can find it. That's coming from the actual estimate that's given in Simpson's rule, which is this quantity right here before we add on the error. So notice you're evaluating f at the nodes, x1, x2, x3, all the way up to x24 in this case. But you have this 1 and then 4, 2, 4, 2, etc. pattern that ends with a 4 and a 1. Those are the coefficients in front of f. And that's what you're seeing in my little right up here. That's the 1, 4, 2, 4, 1, 4, 2, 4, and so on pattern there. Obviously, it's nice to do that using a little script or a program or at least a calculator. And I've just calculated what Simpson's rule would give us here. So he estimates the integral at 0.39430567 and some change. A more exact estimate, and I just went to Wolfram Alpha for this and got like 200 decimal places, as you can do there, is 0.39430605. So you can already see that difference in the 1, 2, 3, 4, 5, 6 decimal place, but the difference is less than 1 part in that 6 decimal place. So if you calculate the error here, it is indeed less than 10 to the minus 6. So we were successful in making our estimate. All right, so hope that helps with homework 17. That's due Wednesday night at 11. As always, let me know if you have questions. As always, stay safe and stay healthy, and I will be back with you again soon. Y'all take care.